Alright, today we're going to talk about periodic trends. So first we have some definitions. So we have atomic radius. Atomic radius is just the size of the atom. And now we measure the size of the atom from the nucleus of two adjacent atoms. So if we have two atoms side by side and their nuclei here, we would measure the distance that way. Okay? And that would be the diameter. Okay? But it is 1/2 of that is the radius, right? So it is 1/2 the distance between the nuclei of two adjacent atoms. Alright, so the group trend, what happens? Well, let's think about in a group. Let's just take group 1, for example. So what happens as we progress down this group? Well, we add an additional energy level. If you recall when we did our Bohr diagrams, which we know is outdated, but it still helps us to visualize. So if we had hydrogen, let's call this little dot our nucleus, it would have 1 energy level. And then we have lithium, it would have 2 energy levels. And then sodium would have 3 energy levels. And so as you add those energy levels, the atom is going to get increasingly larger. So in the group trend is that it increases. Let's go down the group. Right? So which of these atoms would have the largest radius? Lithium, rubidium, or potassium? Right, so rubidium would, because it's further down the group. It has 5 energy levels, whereas potassium has 4 and lithium only has 2. Now the period trend. What happens as we move across the period? Well, as we move across the period, we're adding more electrons into the same energy level. And so what happens is, for example, lithium has 2 energy levels, and beryllium also has 2 energy levels, right? But beryllium has 4 positive charges, and lithium only has 3. So those extra positive charges pull in on 4 electrons, whereas lithium is pulling in on only 3 electrons. So the more pull to the center, the smaller it gets. Smaller because of more pull. Kind of like magnets. The more magnets you put, the stronger their pull is. And so that pull to the center makes the atom get smaller. So as we add more electrons into the energy level, the atom gets smaller. And so it decreases to the right. And again, that's because as you add electrons into the same energy level, there's a greater pull to the nucleus, making the atom smaller. Okay. So which of these would have the smallest atomic radius? So again, if it decreases to the right, we want the one that's smallest to be the one furthest to the right. So we have beryllium, nitrogen, and fluorine. So fluorine, being furthest to the right, would be the smallest. Beryllium's furthest to the left, so it would be the largest. Ionization energy. The definition for ionization energy is the energy required to remove an electron from the outermost energy level. Right? And one of the last videos, a couple of videos ago, we talked about how we make ions, and that we form ions by either adding or taking away electrons. And so we do that in order to achieve a noble gas configuration. So, because noble gas configurations are very stable. Having that full energy level makes it very, very stable. And so if we have, let's say, lithium, right? Lithium has two options. Lithium can lose one electron, have the same configuration as helium, or it could gain 1, 2, 3, 4, 5, 6, 7 to be like neon. And the elements, like everything else in nature, wants to do what takes the least amount of energy. So it takes the least amount of energy to remove one that would to gain 7 more. Besides that, it'd be very difficult for lithium's 3 positive protons to attract 7 more negative electrons. It just doesn't have enough positive pull in order to add that many. So lithium's going to very freely allow electrons to be removed because it wants to achieve this noble gas configuration. Likewise with beryllium, it too will want to do that. Okay? A little less than lithium because it's going to have this full subshell right here. But it still doesn't want to have to, it still would want to get to this noble gas configuration. And then we have boron. It would require a little more energy than lithium or beryllium because again, it wants to get over here, okay? But there's 3 electrons to remove, so it takes a little more energy. Right? Once we get here to 4 carbon, it can go either way. It can lose 4 or it can gain 4. Okay? So its ionization energy is going to go a little higher. Alright? But then as we get over here past there, we're going to nitrogen would have to lose 5 or just gain 3. So it would rather gain 3, so it doesn't want to have any removed. So its energy is going to get higher. And likewise with oxygen and fluorine. And then of course neon's going to be the highest ionization energy in this period because it is stable and does not want any of its electrons to be taken away. Okay? So, a little bit about ionization energy. So let's look at the group trend. Well, if we think about the group, as we go down the group, we'll just look at group 1 again. We talked before that as we go down this group, the atom gets larger. Well, what is it that holds electrons in an atom? Right, it's that positive nucleus. Well, if that outermost electron is far away from the nucleus, then it's going to be very easy to remove it. But if it's really close, like in the case of hydrogen, right, it'd be much more difficult. So if we were to compare hydrogen and let's say, we'll have 3 energy levels there, sodium, right, to remove hydrogen's electron very close to the nucleus would be much more difficult than being able to remove sodium's, which doesn't feel that pull nearly as much because of the distance away from the nucleus that it is. Again, think about magnets. The closer you hold magnets together, the stronger that pull. But as you pull them apart from each other, that pull is less. Right? The further those magnets are, they don't feel that attraction any longer. So the group trend is that the ionization energy decreases down the group. And again, that relates back to the size. Okay? This is inverse to the size. Larger size, larger atomic radius, smaller amount of energy to remove. Okay? So you might want to make a note. This is inverse to the atomic radius. Okay? Alright, so which of these will have the highest ionization energy? Now remember, we just said it decreases down the group. So the further down you go, the less the ionization energy is. We want the highest ionization energy, so we want the one that's furthest to the top. Or another way to say that would be the one that has the smallest atomic radius. Right? And so we have lithium, potassium, and rubidium. And so in this case, highest will be lithium. Alright, now the period trend. when we're just talking about that removal of electrons, we were talking about it across the period. And so as we talked about it, remember we said that neon does not want to lose its electrons at all because it's perfectly stable with its full energy level. And as we move away from neon, that becomes less true, and they're more willing to give them up to achieve the noble gas configuration that preceded them. And so as we move to the right across the periodic table, the ionization energy increases because it becomes more difficult to remove them. The other reason it becomes more difficult to remove them is that, remember we said they get smaller as we move to the right. And so again, if a smaller atom is going to be, an electron is going to feel the pull of those protons much more tightly. And that's going to be held much more tightly and therefore be much more difficult to remove. So the ionization energy increases to the right. Okay, so which of these would have the lowest? So if it increases to the right, the lowest would be the one furthest to the left. So we have B, E, N, and F. So the lowest would be beryllium. And again, we can relate this all back to size, right? The lowest ionization energy, right, is going to be the largest atom. And so between those, the largest atom was beryllium. Alright, so next we have electronegativity. Electronegativity is the ability to attract electrons. So what kind of atoms do you think could attract electrons easily? That's right, smaller ones. Smaller atoms can attract electrons better. And again, that's because their nucleus is more able to put forth that attractive force for those electrons. Electrons can feel them better because there's not so much space between them. Okay? So within the group, right, remember atoms get larger as we go down. So as we go down, if it's a large atom, that nucleus is what we call being shielded. Their nucleus is here, and so you have 3 energy levels as compared to 1. And I have this electron sitting out here. The one that's going to be able to attract it the best is the one that has less energy levels to get through in order for that electron to feel those positive protons. Whereas this one has all these electrons in between that are in the way of this nucleus being able to attract that electron. So electronegativity decreases down the group. And again, that's because the nucleus is shielded by more electrons. And so the nucleus is unable to attract. Alright, so between sodium, potassium, and francium, which would have the highest electronegativity? Well, if it decreases down, that means the higher electronegativity is further to the top. So which of these is furthest to the top? Sodium. Okay. The period trend. Again, if we go back to size, right? As we go to the right, the atom gets smaller. If the atom is smaller, that nucleus is more able to attract electrons. Okay? More able to attract electrons the smaller it is. And so it increases to the right. Except that we have one little problem. We have these noble gases over here that don't have any room